there, my name is Simren Bindra. I'm a junior at Harvard Westlake School, and today I will be presenting my project called The Long-Term Environmental Impact of Wildfires, the Persistence of Lead Contamination 1 year after the Eaton Fire. This project investigates whether lead contamination from the 2025 Eaton Fire presents in soil and vegetation 1 year later. I sampled 20 sites along a 5-mile transect from the fire origin. Soil lead ranged from 12 to 350 milligrams per kilogram, averaging 79.55 milligrams per kilogram. Vegetation lead correlated with soil lead, and the highest concentrations were near the Eaton Wash and a school road. This shows wildfire-related lead contamination still persists. My question was, how do distance and elevation from the Eaton Fire burn zone affect soil and vegetation lead levels 1 year later? Independent variables include distance from the fire elevation, and dependent variables include soil and vegetation lead concentrations. Wildfires release lead from burned structures. Lead persists in soil, can travel in smoke, and causes health effects. Few studies track soil lead long-term after urban fires. I hypothesized that 1 year after the fire, soil and vegetation would still show lead concentrations above the 15 milligram per kilogram background. This is because lead doesn't degrade and can redeposit in surrounding soil. I used PPE, collected soil with scoops, and recorded GPS, elevation, and distance. Vegetation samples were collected where available, and samples were analyzed in an EPA-certified lab using acid digestion and spectroscopy to measure lead levels. Here is a map of sampling sites that I carefully curated after analyzing the geographical factors of many locations that may have burned down, hence their non-existence on the map because they do not exist anymore. This shows our sampling process with full PPE and careful labeling to ensure accurate data. In the top right over here, this graph shows soil lead versus distance from the foothills. There isn't much of a clear pattern with distance, though higher levels appear near the burn zone. This graph in the bottom left shows lead versus elevation. Lead increases downhill from the fire, suggesting gravity or runoff effects. Some key numbers are that soil lead was from 12 to 350 milligrams per kilogram, an average of 79.55. There were 16 sites under 100 milligram per kilogram, and 4 with moderate risk having 100 to 400 milligram per kilogram. Vegetation lead strongly correlated with soil lead. In the bottom left over here, this map shows soil lead across the Eaton Fire zone. Notice wide variability with hotspots near a school road and Eaton Wash. This graph over here shows soil versus vegetation lead. Higher soil lead corresponds to higher vegetation lead, showing ecological incorporation. Some things worth noting are the highest soil lead levels were 350 milligrams per kilogram near the school. Second highest was 260 near Eaton Wash, and there were moderate levels at parks and schools. Average soil lead exceeded the background level. Spatial trends show higher concentrations downhill. Vegetation lead correlates with soil lead, and isolated hotspots suggest wind, topography, and traffic influence deposition. Even one hotspot is a long-term exposure risk. The data support our hypothesis that lead contamination does persist 1 year after the Eaton Fire. Elevated levels were observed near schools, parks, and downhill from the burn zone, and vegetation accumulates lead, posing ecological risks. Continued monitoring and remediation are necessary to reduce these long-term exposure risks. What I learned are that wildfires have lasting environmental impacts and lead persists long after the fires. Next steps include increasing sampling, multi-year monitoring, and developing portable soil lead detection devices to guide public health decisions. Thank you for listening to my presentation, and I hope you enjoyed. Bye!